Welcome back to Honors Calculus. In this video, we're going to be talking about relative extrema. We've talked about the idea of extrema previously. You know that if you are thinking about a curve, the extrema are the places where locally the graph reaches a maximum or a minimum value. I like to think about the extrema as the turnaround points, the places where the graph goes from increasing to decreasing, or where the graph goes from decreasing to increasing. We also know that the extreme values must occur at critical points, places where the derivative of the function is either zero or undefined. Thinking back to things you've studied in previous mathematics courses, you've previously learned how to graph, say, a polynomial function by plotting its x-intercepts and then trying to track what's happening with the end behavior. Maybe you also looked at the y-intercept to try to get some sort of scale for how big the thing is going to be vertically. But the idea here, the thing that I want to look at today, is how much easier this process would be if you just got a little bit of additional information. If you knew the y value of the maximum and the minimum of the function, you would be able to graph it that much more easily. And so that's what I want to look at here. Let me go ahead and get my head out of the way, and let's take a look at a relatively simple polynomial. Right, I'm giving us this polynomial in factored form, saving us a little bit of effort. We don't have to factor the polynomial ourselves in order to figure out what the x-intercepts are. Right, we know that we can find the x-intercepts by setting this thing equal to 0 and using the zero product rule. That will give us that x plus 1 is equal to 0, which means that x is -1, and we have an intercept at -1, 0. That will give us that the next factor, x plus 3, is equal to 0, which means that x is -3, and we have an intercept at -3, 0. And then the third factor, x minus 2, could be 0, which means that x is equal to 2, and we have an intercept at 2, 0. We can figure out what the end behavior is. We can figure out what the y-intercepts are if that's something that you really want to do, but I don't think it's all that useful. Instead, what I want to do is look for the extrema. And in order to do that, we're going to need to take the derivative, and polynomials are much easier to differentiate when you multiply them out. So let's see, x plus 1 times x plus 3 is going to be x squared plus 4x plus 3. And then if I multiply that times x minus 2, let's see, multiplying everything times x will give me x cubed plus 4x squared plus 3x. Multiplying everything times minus 2 is going to give me minus 2x squared minus 8x and minus 6. And if I bring all of that together, I get x cubed plus 2x squared minus 5x minus 6. All right, we can pretty quickly find the y-intercept here. It's going to be the point 0, -6, but I don't care. I'm looking for the extreme values, so I'm going straight into the derivative. Differentiating a cubic polynomial is fairly straightforward. Derivative of x cubed is 3x squared. The derivative of 2x squared is 4x. The derivative of minus 5x is minus 5, and the derivative of minus 6 is 0. Our derivative here is a polynomial. So the critical values are all going to be occurring when this polynomial is equal to 0. Right? Polynomials are never undefined, so we don't have to look for critical values where the derivative is undefined. I could try solving this by factoring, by using completing the square. See, 3 times -5 is -15. I don't think there's anything that multiplies to -15 and adds to +4. So I'm going to jump right to the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4 times a times c. 4 times 3 is 12. 12 times 5 is 60. Minus a minus is plus. All over 2 times a, which is 3. 2 times 3 is 6. If I want an exact value solution, I could go from here. And oftentimes that is useful. So working through quickly, notice that we can factor here. 76 is actually divisible by 4. If you take 4 goes into 76, 4 goes into 7 once, leaving behind 36. 4 goes into 36 9 times. 76 is 4 times 19. So we can reduce that square root and write it as the square root of 4, which is 2, times the square root of 19. Now a bunch of common factors of 2 are going to cancel each other out. And we can write this solution as -2/3 plus or minus 1/3 square root of 19. Right, that's something that you should remember from a previous mathematics course. But if you don't, it's not that big of a deal. In this particular context, we're not really looking at finding the exact value of the extrema in order to report on that. We're looking at finding a point on the coordinate plane so that we can graph it. So instead of thinking about this in terms of exact values, I'm going to turn to my calculator and have it do the work for me. All right, so going up to before I did any work, because if I made a mistake, that will avoid it. We have -4, I guess I need this in parentheses, -4 plus the square root of 76, close the square root, close the numerator, all divided by 6. My calculator tells me is 0.786, etc. That's something in the ballpark of 0.8. Again, I'm trying to graph with this, and the difference between 0.786 and 0.8 is not something I'll be able to notice when I'm graphing by hand. Right, then going up and editing this so that I'm subtracting instead of adding, I'll get my second solution, -2.119. Again, the difference between 2.1 and 2.119 is almost negligible as far as trying to actually graph something. All right, now that we're done with the calculator, let's get it out of the way. I'm going to scroll up here a little bit. I'm going to grab my original function so that we can keep working with it. And now we need to go back to the calculator. I'm going to take both of these and plug them in. I'll evaluate f of 0.8 and I will evaluate f of negative 2.1. Again, rounding to the point of this is something I can actually graph, not worrying about exact values, because all we're looking for is drawing a picture. Exact values don't help us draw a picture. All right, so bring my calculator back, and let's take 0.8 to the third power plus 2 times 0.8 squared minus 5 times 0.8 minus 6. My calculator tells me is something in the ballpark of negative 8.2. And then plugging in negative 2.1 for x, we'll have negative 2.1 cubed plus 2 times 2.1 squared. Remember, the square of a negative is a positive, so I can save myself a little bit of effort by remembering that and plugging it in without worrying about the negative sign. And then we'll have minus 5 times negative 2.1. I could have changed that to plus 5 times 2.1, but I didn't think of it until after I typed it in. And then minus 6 gives me something in the ballpark of 4.1. All right. And with that, that's really everything we need from our calculator. So let's get the calculator out of the way one more time. We have these 2 points, 0.8, negative 8.2. We have the point negative 2.1, 4.1. These might be maximums, these might be minimums, these might not be anything. We'll be able to figure that out by looking at them on the graph. All right, so scrolling back up one more time, we are going to need these three x-intercepts, negative 1, 0, negative 3, 0, 2, 0. Yeah, I can copy those. And paste them down here with everything else. I guess I'm going to need quite a bit of space downward. All right, so negative 1, 0 is right there. Negative 3, 0 is right there. 2, 0 is right here. Negative 2.1, positive 4.1 is somewhere in the general vicinity of that. And 0.8, negative 8.2 is somewhere roughly in the vicinity of that. And we can see that this point, which we thought might be an extreme value, from here the function has to go down to this point and down to that point. There's no other possible extreme values near it. So by process of elimination, that must be the maximum. And likewise, this point down here that we said might be an extreme value, the function must go up to this point and must go up towards this point. There's nowhere it can go downward from and no other points near it that could be the possible extreme values. So by process of elimination, the function must be curving upward, looking something like that. Right? That automatically gives us the end behavior. There's no other turnarounds anywhere. That automatically gives us the y-intercept, or something that's pretty closely resembling it. 1, 2, 3, 4, 5, 6. Yeah, something pretty close to that. And so we can graph our functions using the intercepts and the extrema and get a more precise result, a more carefully accurate graph than we can with intercepts alone. Right. But thinking about that picture gives us another tool we can use for thinking about relative extrema. When you have a relative maximum, you know that on either side of the maximum, the function is going to be decreasing. When you have a relative minimum, you know that on either side of that minimum, the function is going to be increasing. I'm sorry, right? We increase up to a maximum and then we decrease away from it. We decrease down to a minimum and then we increase away from it. And so just thinking about that is actually enough information for us to figure out what kind of extreme values we're going to have. So let's look at something a little bit messier. G of x is negative 3x times the square root of x plus 1. And we want to look for relative extrema again. This time, I'm not going to plan to take that next step of graphing the function. I'm just looking for the relative extrema. And so I'm going to start off the same way I did before. I'm going to take the derivative. If we could simplify this, it would be nice, but unfortunately with the square root, there's really not a lot we can do. I'm just going to have to go at this using the product rule. The derivative of the product of two functions is the derivative of the first function multiplied times the second function, plus the second function, the first function times the derivative of the second function. The derivative of the square root of x plus 1 is 1 over 2 times the square root of x plus 1. And we can try to clean this up, find some common denominators. This actually looks a lot messier than it really is. But on that first term, multiply numerator and denominator by 2 times the square root of x plus 1. The square root of x plus 1 times the square root of x plus 1 is x plus 1. And doing that gives us a common denominator. We can clean up in the numerator. Giving us a relatively simple expression to work with. One thing that I want to specifically draw attention to here is that our original function is defined whenever x is greater than or equal to -1. And our new function is defined whenever x is greater than -1. There are a lot of places where the derivative is not defined, and where the derivative is not defined could be critical values. But if the original function isn't defined there, then it's not really that much of an issue. It's not something to think about. But the one point where the function is defined and the derivative is not is when x is equal to -1. G of -1 is going to be -3 times -1 times the square root of 0, which is 0. G prime of -1 is going to be whatever in the numerator times 2 times the square root of 0. So we're, excuse me. So we're dividing by 0 this time, and dividing by 0 is undefined. right? So x equals -1 is a critical value for the function. And then the other critical values happen when the derivative is equal to 0. In this case, that means that that numerator is 0. -9x minus 6 is equal to 0. And we can solve this pretty quickly. -9x equals 6, x equals -6/9, which reduces to -2/3. All right. And so I'm going to test the first derivative. Another thing to think about with critical values, with the first derivative in general, right? When the first derivative is negative, the function is decreasing. When the first derivative is positive, the function is increasing. And when the first derivative is 0, the function has leveled off, even if it's for an instant. And that's where we find our extreme values. So we know where the first derivative is 0. It happens at -1, or undefined at -1, 0 at -2/3. Everything in between is going to be the same, either always positive or always negative. So choose a value somewhere in the middle here. Right? There's not a lot of space between -1 and -2/3, but there is some space. Right? -2/3 is -0.667, so something like 0.75, -3/4 will work. And then pick something that's to the right of -2/3. Everything over here is going to have the same value, either always positive or always negative, because it can only change between positive and negative if it goes through 0 or it's undefined, and we know everywhere that that happens. Whenever you can test at 0, I always encourage it. 0 is an easy thing to work with. All right, so I want to evaluate g prime of x, which again, remember, it's just off screen here. -9x minus 6 over 2 times the square root of x plus 1. I'm going to evaluate g prime of -3/4. And I'm not going to worry that much about what I get here. I'm just going to worry about whether it's positive or negative. All right, so I'm going to take -3/4 times -9 and then subtract 6. All right, so 3 times 9 is 27. 27 divided by 4 is really close to 7. -3/4 plus 1 is positive 1/4. All I care about is that that's positive. Right? Again, that's not actually 7. It's something a little bit less than 7, but it's bigger than 6, and that's all that matters because that means we're going to get a positive result. All right? Then I'm going to test when g prime when x equals 0. So it's going to be -9 times 0, which is 0 minus 6. And then we'll have, right, square root of 0 plus 1. 0 plus 1 is positive. Again, positive is all that I care about. 0 minus 6 is negative, and negative divided by positive is negative. So the function is increasing in this region, and it's decreasing in that region. Which means that when x equals -1, we have a relative minimum, and when x equals -2/3, we have a relative maximum. right, we'll wrap up as we often do with a problem for you to try. Let's take a look at the function. Well, we've used f and g. I guess this is going to be h of x. H of x is x over x minus 7. So I would like you to look at this function, find all of the critical values for this function, and then use the first derivative test to determine which of those critical values are relative maximums, relative minimums, or neither. I didn't mention it up until this point, but before I wrap up here, I do want to stress that it is entirely possible for a critical value to be neither a maximum nor a minimum. That will look like the function is increasing both before and after, or that it's decreasing both before and after. It's something that can happen. It certainly will happen. Whether or not it happens here, I'm not going to say. I want you to take a little bit of time to play through that and see what you come up with on your own. All right. See what you can do with that one, and I'll see you in the next video.